Yeah, welcome everyone to the last talk of this semester by Robert Kusk. He will speak about Affine Schubert varieties or splinter.
Yeah, okay. Well, thank you for the introduction. It's a pleasure to be here. Yeah, so I'm going to explain that Affine Schubert varieties are splinters. I'll tell you what all these words mean, and this is joint work with João Lourenço. And just please feel free to interrupt me with questions at any point. So I want to start by just defining Schubert varieties really fast. Okay, so for now, K is going to be a field, and I'm going to pick G over K, a split reductive group, and I'm going to fix a maximal torus and a Borel. Okay, and so a Schubert, well, before defining Schubert varieties, I should tell you the flag variety is just the quotient G mod B. Okay, and this is a smooth projective variety. So, for example, you could take G to be GLN, you could take B to be the upper triangular matrices, and then this quotient is called a flag variety because it parametrizes flags in a fixed vector space. Flags being a descending sequence of subspaces where each relative quotient has dimension 1. Okay, but you can do this with any split reductive group. And Schubert varieties are going to be orbit closures for the left action of B inside acting on G mod B. So for example, to enumerate these things as sets, the double quotient space G mod B mod B, this is naturally in bijection with the Weil group. So as a group, it's the normalizer of your torus modulo T, and this is a finite group. So I'm going to usually denote it by W, and this is called the Weil group. Okay, so for example, if G is GLN, representatives for these double cosets are just permutation matrices, and the Weil group is the symmetric group on n elements in that case. Okay, so I can define Schubert varieties. So if I have an element W in the Weil group, the Schubert variety is just the closure of the left B orbit. So the Schubert variety, I'm going to denote these by X sub W, okay? And this is just, I take BWB mod B, take the closure, and this lives inside this flag variety. While the flag variety is smooth, in general, these Schubert varieties are singular. Okay, and so I want to tell you a little bit about the singularities of Schubert varieties. And so there's been a lot of work on the singularities of Schubert varieties, and so I want to particularly highlight work of Mehta and Ramanathan. There's actually a series, I think, of like 3 papers, but they're all around 1985. So, yeah. Okay, so Mehta and Ramanathan, they showed the following. Again, these things, some of these results were known by other proofs, but I want to talk about their proof. Okay, and so they showed that each of these Schubert varieties is normal, Cohen-Macaulay, they have rational singularities, and the main property that I want to talk about today is also Frobenius split. So if the characteristic of K is positive, and maybe say K is also perfect, then XW is what's called Frobenius split, and I'll probably just abbreviate this F split from now on. And I'll give you the definition now of F split. Okay, yeah, so, and in fact, the way their proofs go, essentially the other properties are deduced from the Frobenius splitting. So the way they prove this Frobenius splitting, it gives them a new proof of these previous results. Okay, yeah, so from now on, I'm going to assume the characteristic of K is positive. And just for simplicity, I'm going to assume K is algebraically closed. Okay, so I'll give you the definition now of a Frobenius split scheme. So a scheme X over K is F split if the Frobenius map can split. So what that means precisely, F split if there is an OX linear splitting to the Frobenius. And so the Frobenius map, I'm always going to view it as the map from OX to the push forward of OX along the absolute Frobenius. Okay, so this is the sheaf of abelian groups on F lower star of OX is the same, but the module structure is twisted. When you multiply it by an element of OX, you have to scale it by the pth power. So there's an OX linear map, which just sends a section to its pth power. Right? And being Frobenius split just means that there is a section phi taking you back down to OX such that the composition is the identity. Okay, so turns out Frobenius splitting is kind of rare for projective varieties. So let me give you a quick example here. All right, so for example, the projective line P1 is F split. Okay. But so to construct a splitting, I mean, in the most naive way, you would have to work on some affine coordinate charts and construct a splitting over each chart in such a way that they're compatible. So, for example, inside P1, you have the affine line, spec of Kx. And so if you wanted to construct a splitting there, what could you do? Well, you could observe that, right? If I want to send some monomial with just one power of x, what can I do here? Well, I'm going to have to take the pth root of a, which I can do because k is perfect. And then in general, I'll take this. So this is one splitting that works. I can do this if p divides I and 0 else. So what's really happening here is when x is just a1, this f lower star of OX is just a free module with basis 1 x up to x to the p minus 1. So you have a lot of choices for splitting locally. And well, because P1 is nice, it has this one element x in the fraction field that has essentially no relations. You can do the same thing over for GM and these things glue. Okay, so P1 is F split, but in general, it's pretty rare for a projective variety to be F split. So if X is, say, a smooth projective curve, and say the genus is at least 1, and then X is F split if and only if the genus is 1 and X is an ordinary elliptic curve. This is F split if and only if G is equal to 1 and X is ordinary. So what's going on here with ordinary? If you have an elliptic curve, well, anytime you have a splitting to the Frobenius map, you can just take cohomology of this sequence. And so in particular, the Frobenius map would have to be injective on H1, but that certainly requires your elliptic curve to be ordinary. Supersingular, one definition is that map on H1 is 0. So, okay, so it's rather rare for smooth projective curves to be Frobenius split. Okay, and so what are some applications? Why would you care about having a variety that's Frobenius split? So in the context of Schubert varieties, one is interested in constructing representations of the algebraic group G. And one of the best ways to do that is to take cohomology of line bundles on G mod B. The algebraic group G acts on those line bundles, and this gives you lots of interesting algebraic representations of G, and in particular modular representations if you're working in characteristic B. Okay, and so application, well, it's immediate from, so it's not difficult to show using the fact that you have a Frobenius splitting. All right, so first of all, if I have G mod B, and I take any ample line bundle, so L ample, this is an algebraic representation of the group G, and you just, because G mod B is Frobenius split, you can show that this is 0 I is greater than 0. So this is very close to what is often called Kemp vanishing. Kemp vanishing is just a little bit stronger than this. And actually, before the work of Mehta and Ramanathan, Anderson and Habush gave 2 independent proofs of Kemp vanishing, still using Frobenius splitting techniques. So it's Frobenius splitting is very useful because it gives vanishing for line bundles, and from the perspective of representation theory, this is very useful when you're working with exact sequences. Okay, so now I want to talk about affine Schubert varieties, which are sort of a number theoretic analog of ordinary Schubert varieties. So okay, so the setup here, I'm going to take E to be the Laurent series field in one variable. O will be the ring of integers, which is power series in that variable T. And I'm going to take now a quasi-split reductive group over E. In particular, it has a Borel, and I can also talk about parahoric models. So I'm going to use the same notation because somehow the combinatorics is basically the same in the affine case. So I'm going to take B to now be an O group scheme, which is a parahoric model. And that means in particular that when I invert T, B mod O is just this group G that I started with. Okay. All right, so for example, I could take G to be GLN, G to be GLN, and I could take B to be the Iwahori subgroup. And this is a group scheme over O, whose O points are precisely matrices that are upper triangular mod T. So I have anything going on above the diagonal, but then below that, everything has to have a T in it. Okay.
Sorry, there seems to be a typo.
Oh no, what's my typo?
Base change to E.
Oh yeah, this should be switched. Thank you. Yeah, E base change to E. Thank you. Yeah, okay, so for example, you can just take the Iwahori, and so again, the left B orbits inside G mod B are parameterized by some nice set. And so in this setup, you can still make sense of the quotient G mod B, called an affine flag variety. And it has the structure of an end projective scheme. And end projective, and it's still a case scheme. Okay. Yeah, so this is usually called the affine flag variety. The reason it's an increasing union of finite dimensional projective varieties. It's so large because I want this to be an object over K, whereas my group starts over E. But okay, so it's still a nice object to work with. And this double quotient, so B mod G mod B, I'm going to again denote this by W, and this thing is usually called the Iwahori file. So when my group is simply connected, this would really be an affine file. Okay. And you can still define a Schubert variety, an affine Schubert variety, just to be a closure of an orbit here. So maybe I'll do that down here. So yeah, XW, it's again just the closure, BWB mod B inside G mod B, right? And this is what I would call an affine Schubert variety. Okay, so yeah, maybe just a quick. Why are affine Schubert varieties interesting? Well, from a number theoretic perspective, they show up in several places. Let's see. So one place they show up is they show up in local models of Schubert varieties. I'll just mention that. Okay, so why do people study affine Schubert varieties? So there are many reasons, but one reason is that these XW, they appear in local models of Schubert varieties. So Schubert varieties, by local model, I mean something defined over, say, mixed characteristic DPR like ZP. The singularities are supposed to model those of a given Schubert variety. And so these affine Schubert varieties, they appear in both the generic and special fibers of these local models. And the special fiber, they appear in sort of a more complicated way. The special fiber of the local model is some kind of complicated union of Schubert varieties. It's not irreducible in particular. Okay, so that's one place that these affine Schubert varieties appear. And also from the perspective of the Langlands program and geometrizations of the Langlands program, using using affine Schubert varieties or affine flag varieties allows you to upgrade certain Hecke algebras. So, for example, you can look at the convolution Hecke algebra functions on G mod B mod B. This would usually be called a Hecke algebra, but with these Schubert varieties, you can then upgrade this to a category of sheaves on this double coset space, and this might be called like a Hecke category. Okay, so these sort of categories occur all throughout the geometric Langlands program and in other geometrizations of more arithmetic Langlands programs, such as in Vincent Laforgue's work and Fark-Schulz's work. So I think I actually have a piece of paper board. I'm going to write down a table of some previous results about the singularities of affine Schubert varieties. I'll state our results. Any questions while I'm erasing? Okay, so yeah, so here are some previous results. Right, and so for all of these results, I have to make small technical assumption, which is that the prime P does not divide the order pi1 of the derived subgroup. This really is a minor assumption. Somehow you have to have P not dividing this so that your Schubert varieties are normal. And somehow normality is the only obstruction to all of these other nice properties that I'm going to write down. Okay, and so I'm going to make a table here. I'll probably have to go over to the other board. The property, the assumptions on the group, and I'll tell you who did this. Continue over there. Okay, yeah, so this is about properties of the affine Schubert varieties. And so the first thing that was proved is that these are Frobenius split. And this also, just as in the work of Mehta and Ramanathan, can be used to get normality and Cohen-Macauliness. But so Frobenius splitting is what I want to focus on. This was originally done for split and simply connected groups. And this was done, I think, around 2003 by Faltings. And then, okay, the same property for Frobenius split. This was extended to affine Schubert varieties for any tamely ramified group, meaning a group which splits over a tame extension of the field E. And this was done by Pappas and Rappaport around 2008. Okay. And let's see here. So yeah, I can get one more in this table. And then now going back to the non-affine case, just the ordinary flag variety. So non-affine was shown by Lauritsen, Robin Peterson, and Thompson in 2004 that ordinary Schubert varieties are what's called globally F-regular. I'll give you the definition of that here. So, okay, I'm running out of room. So the names were Lauritsen, Robin Peterson, and Thompson. And I think this was around 2004. Let me maybe go over somewhere and give you the definition. Yeah, let's go over here. Oh, right there. Okay, yeah, so what is globally F-regular? So it's sort of like an abundance of Frobenius splittings. Or precisely, you're globally F-regular if for any effective Cartier divisor D, you have a splitting of the following form. So you always have a map from OX to OX twisted by D. And then you can apply the Frobenius to this. And for global F-regularity, you might have to apply some power of the Frobenius. So an eth iterate Frobenius. Okay. And being globally F-regular, you should always be able to find a splitting back here, back going down to OX, where the composition is the identity for E sufficiently large. Okay. So it's some kind of abundance of Frobenius splittings relative to all effective Cartier divisors. Is this right? I think this is right. It doesn't look right.
The first map factors as it splits, which it surely doesn't. It's like multiplying locally.
So you go into here and then you raise to the p. So this should be the composition which sends you to like your section here plus also something to the p to the eth power. Is that all right?
Sorry, but if the whole thing splits, then that means that the first map splits. Which locally is saying that multiplication by a coordinate is split injective, which it's definitely not. I think you want to have a second term there and then have the D be on the inside of the F lower star.
Okay. So maybe I just want to, okay, thank you. Okay, yeah, I think you're right. Okay, yeah, so but this is just the map which sends, this sends like a section A to the P to the E times S, where S is the section of it. Okay, thanks. Yeah, okay, so that's what it means to be globally F-regular. Okay, cool. And
sorry, I mean, first, I assume SC just means simply connected here.
yeah, simply connected, yeah.
And sorry, maybe I'm missing something. What does it mean to be non-affine and reductive?
Oh, I mean, like not affine in the sense that not working over this E, just working over K itself. Okay. Like the stuff I did at the very beginning.
I see.
Like you could call it the finite flag, right?
Okay.
Yes.
Yeah.
Perfect. Any other questions? Okay, cool. Yeah, okay, so so I'm going to continue this table here. So same sort of rows. Okay. Okay, yeah, so again, in the affine case, so in my thesis, I showed.
Can I have one question?
Yeah, sure.
Because this work of Habush and Anderson that you mentioned on the Wolfram theorem, I kind of thought that this being globally F-regular kind of follows from what they do, that you have this one effective.
Oh yeah, so I should mention that, yeah. So the way that Mehta and Ramanathan and all of these other people do the Frobenius splittings, even in the finite flag variety case, they actually get global F-regularity, even though the term didn't exist back then, because they show that you actually have a splitting compatible with all Schubert subvarieties. And so they actually did get this result. It just didn't really exist. So that's essentially what I observed in my thesis, is that actually do have global F-regularity. And so this was for G split. And this really, it follows essentially from the splittings constructed here and the method of Mehta and Ramanathan. But it turns out that when you have a non-split group, you have to do a little bit more work. And so, yeah, okay, so also globally F-regular, just write that. And this was done for almost all groups, but they had to exclude one case. So if P is equal to 2 G has to be not a ramified odd unitary group. Okay. And this was done by Frobenius, Haynes, Lourenço, and Richards in around 2022. Yeah, so somehow all of the proofs before this are sort of uniform, but when you have wild ramification, there's a lot of casework you have to do. And I'll say something about why they couldn't do this one particular case. Okay, and so by the way, why would you, well, I mean, there are a lot of reasons that global F regularity is interesting, but one reason that I was interested in global F regularity is that it implies that the mod P intersection cohomology is a constant sheaf. So if X is globally F regular, deduce that, so there's a theory of intersection cohomology with mod P coefficients, and if you're globally F regular, the constant sheaf is the intersection cohomology. Okay. All right, cool.
But it's much stronger. Right?
Oh, it's much stronger, absolutely.
It just needs local.
Ethnopotence is for the converse, yeah. So in fact, yeah, it's enough to be F rational or even just ethnopotent. But it turns out that all of the proofs of these things for Schubert varieties, the ones that really work for all groups, actually go through global F regularity. Somehow it's actually much easier to give a global proof than to try to argue locally on these things. Yeah. Any other questions?
Could you maybe say a little about how you go from F regularity to something about intersection cohomology?
Yeah, so this is okay, so this is for Étale sheaves with mod P coefficients. And so, well, you always have the Artin-Schreier sequence, which relates the structure sheaf to mod P Étale cohomology. It's the kernel of Frobenius minus identity. So somehow mod P intersection cohomology being constant is a statement about the stocks and co-stocks vanishing in certain degrees here. And when you apply the Artin-Schreier sequence, that relates these stocks and co-stocks to the action of Frobenius on local cohomology. And global F regularity in particular implies that, well, it implies Cohen Macauliness, which gives you a lot of vanishing. And then it implies also just what you need in the top local cohomology to get the necessary vanishing result. Yeah. Other questions? Okay. All right, so now I want to talk about what we prove that's different from these results. Okay, so maybe I'll go up here.
So this is a somewhat random question. I
Sure.
feel free to not answer. But if I was working in Kersig 0,
Yeah.
is there some analog of this property where now you talk in terms of mixed Hodge modules? And
Which property?
this last thing.
Oh, this is the thing. I'm not sure. I would love to discuss more about that. But yeah, like in mixed characteristic, is there some sort of analog of being like rationally smooth? Is that sort of the question? I'm not really sure, but
Sorry, in Kersig 0,
yeah.
These are, I assume, not rationally smooth.
Oh no, definitely not. Yeah.
Right, I was imagining more like you only demand like the Kerr 0 of the Hodge theory sort of works like that, smooth variety.
Right. Yeah. So okay, yeah. So these Schubert varieties, yes, their intersection cohomology in anything but mod P coefficients is more complicated, certainly. Yeah. So it seems very difficult to. I would love a statement that sort of relates characteristic 0 to characteristic. I'm not exactly sure what that should look like. Yeah. Okay. So. All right. Yeah, so in the non-affine case, so that means back to flag varieties as I defined them just at the very beginning. Bhatt gave a totally new proof of these sort of properties back in around 2011, I think. So in the non-affine case, Bhatt, let's see, let's divide this. This was around 2011. He showed that GLN mod B, the full flag variety, is what's called a splinter. But what's interesting is this was completely different from these previous proofs. I'll tell you what a splinter is in a minute. And basically our result is that you can extend Bhatt's methods and come up with the proof that all affine flag varieties are splinters. So theorem, this is joint with João Lourenço. Okay, this was earlier this year. So no assumptions on G are needed. This can be affine, non-affine, be wildly ramified. No assumptions on G, and as long as your Schubert varieties are normal, which is guaranteed as long as P doesn't divide the order of the derived, pi1 of the derived subgroup, the XW are splinters. Okay, so maybe I'll give you the definition of a splinter and then I'll make a few comments about this here. So first of all, the definition of a splinter. So hopefully I will get this one right. A normal scheme, say X over K, is a splinter. So by the way, this you can also make this definition in characteristic 0. If for every finite surjective map can split the map on global sections of O. So if for every y to x finite surjective, maybe I want to assume that y is I probably want to assume that y is also normal. There is an OX linear splitting of basically the same map we wrote down for the Frobenius, but now just using an arbitrary finite cover. So I have the map from OX to F lower star OY, and you should have a splitting phi of this. Okay, so little f is the absolute Frobenius, this is F split. So this is a strict generalization. Yeah, it also works in characteristic 0, but I think in characteristic 0, splinter is equivalent to normality. And even at the derived level, if you work with derived push forwards, I think it's just rational singularities. So it's a totally different theory, characteristic P. Okay. And in fact, derived, same as not derived, is also done by Bhatt in this paper. Okay, so we show that these Schubert varieties are splinters, but we actually show a little more. So I want to make a few comments about this.
Yeah.
Any questions while I erase?
Like if degree is coprime to P, then this is always true.
Sorry, say that again.
If the degree of F is coprime to P, then this is always true.
So this F?
Yeah.
Oh, it's easy to split things. Yes. Yeah. So somehow the only difficulty comes when P divides the order of F. Yes, that is true. Yeah. Okay. So yeah, a few comments. So yeah, so we actually prove something slightly stronger than this. So actually prove a splinter property, again, relative to a divisor, much like in the definition over there of global F regularity for a particular divisor. So we actually prove splinter relative to a particular divisor. And this turns out to be strong enough to rededuce global F regularity. We also get a new proof of global F regularity. Actually, what we really shows, so is there's a mention in a bit, there's another property called globally plus regular relative to a divisor, and that's actually what we show, but I will get to that in a minute. Yeah, so this removes all casework and the one assumption on the group G from the table. So it removes all casework when G is wildly ramified. And then I'll mention also, so the starting point is Bhatt's work, but we need a few tools that were developed later. So I think that probably, if you're just working in characteristic P and not in mixed characteristics, some of these things may have already existed in various forms, but so we use some results from a 7-author paper. I'll write the initials as Bhatt, Ma, Patakali, Schwade, Tucker, Waldron, and Wistasek. I think I got all that right. I think this was around 2023, but we need to use some tools in here that which allow us to work with rational Q divisors in our boundary pair. And I'll say a little bit more about why we need those later on. Okay, cool. So that's what we proved. And now the remaining time, I'll talk a little bit about how we show this. Let's see here. Okay, yeah, so a quick few examples just to orient you the splinter property here. So for example, P1 is still a splinter, but if you have a smooth projective curve, so if genus of x is greater than or equal to 1, it's not a splinter. So you do lose ordinary elliptic curves when you ask for the splinter property as opposed to just Frobenius splitting. And I can tell you the reason is actually quite simple. It's because the multiplication by P map on an elliptic curve always induces the 0 map on cohomology. Okay, so, and actually, we don't directly work with affine Schubert varieties, we work with certain resolutions. So use the following property. Suppose I have a nice proper and birational map. Say probably I need to assume both x and y are normal. Then if the guy upstairs, if y is a splinter, so is x. So y splinter implies that x is a splinter. Okay. So this allows us to work with a particular resolution. Okay, so, but how do you actually go about showing something as a splinter? It seems like it would require quite a lot. You have to show that you can split some map for any finite surjective cup. But it turns out that you can give a cohomological criterion for when you have a splinter, and this is also in that 7-author paper over there. So yeah, so how to show a given variety of scheme X is a splinter. So it turns out that you can just apply some adjunctions. You have growth and Dieck duality for finite maps. You apply Serre duality, and so you can show that have a, well, so given a, let's say here I have y finite surjective over x, you can show that you can, this map splits, so OX to f lower star OY splits, if and only if in a certain trace map, maybe it's the Serre dual of what you could call the trace map. So there is a map in top degree, x, OX, KX, to, yeah, you need the following trace map to be injective. And so this goes to the top cohomology, what y, with coefficients in the pullback of the canonical on x. Okay, so this is just an actual, say I'm working with, you know, say x is projective. So that I'm working with, these are actually finite vector spaces, and so it turns out the splinter property really is just be stated in terms purely of a certain map being projective on. This, I might call this a trace map, or the Serre dual of a trace map. Yeah, and we learned this from that 7-author paper. Okay, so that's the first thing. It actually turns out it's easier to prove the splinter in for projective varieties. Have this very nice cohomological criterion for when something splits. Okay. But this criterion, now we've introduced a complication. We have to somehow be able to compute with the canonical bundle on X. So that's why it's particularly nice to take a resolution of singularities where it is easier to compute the canonical one. And so, yeah, in general, it is hard to get much understanding of the canonical bundle of one of these Schubert varieties. And so instead, we do what people always do, and that is to consider the de Mazur resolutions. So there is a resolution of singularities, d sub w to xw. This is either called de Mazur or Bhatt-Samuelson, depending on where you look. Okay, so this is some particular resolution of singularities, and it's a very nice, smooth variety. It has the structure of an iterated P1 bundle. And so there's a sequence of maps going down that are all P1 bundles. Okay, there are n maps where n is the dimension of xw. And this de Mazur variety, it arises in a combinatorial fashion. So I mentioned this Iwahori-Weil group that indexes the Affine Schubert varieties. So up to translating to the connected component of the identity in the Affine flag variety, you actually have a Coxeter group, and then writing W as a product of simple reflections gives you this de Mazur resolution. But this de Mazur resolution, it has a lot of nice geometry, right? So there are sections of all of these maps going back up. And so you can inductively compute that the Picard group of the de Mazur is just n copies of Z. And so you have a lot of nice divisors and copies of P1 in here. So anytime you omit one of the letters in a reduced decomposition of W, you get a divisor, which is also a de Mazur variety. And if you omit all but one of the letters in a reduced composition, you get a copy of P1. So you have a bunch of P1s floating around. And this isomorphism I've chosen here is given by restricting a line bundle to each of the n canonical P1s living inside the de Mazur. Okay. Okay. Yeah. So what's important here is that, so in our proof and also in the original proofs of Mehta and Ramanathan and so on, there's this particular line bundle, 1, 1, 1. So it's a line bundle that restricts to 1 on each of the n little copies of P1 living inside here. And what's important is that this thing is semi-ample. That means some power is base point free. Great. And so what actually goes, the hard part in the proof of Mehta and Ramanathan is, in order to make their method work, what you need to show is the following. You need to show that for some particular, for some power of P minus 1, you get to pick the E, but you have to look at a power precisely of this form, and you have to show that this is base point free, which is not automatic for being semi-ample. In fact, you just need a section which misses the intersection of all the divisors up here, but essentially what you show is that some particular power is base point free, but this is hard. And the reason it's hard is because all of the proofs of this, and using the Mehta and Ramanathan criterion, involve showing that this line bundle on the de Mazur variety descends to the Schubert variety. You have much greater control of ample things down here. So this is really the hard step. Hard, show that one of these powers descends to an ample line bundle on the actual Schubert variety. This is why this is hard, and somehow when your group is wildly ramified, there's just a bunch of combinatorial casework you have to do, and it turned out that there was just this one particular case that they couldn't get to work. Okay, but so in our proof we can avoid this particular descent argument, and instead it's a lot easier. We really just need the semi-ampleness. So semi-ample, another way of thinking of semi-ample is it's in the closure of the affine cone, or sorry, the ample cone. So it's very close to ample things. All right. Yeah, so the way our proof goes is we imply an inversion of a junction in that 7-author paper. So inversion of a junction it's just a word for a criterion for extending a property from a divisor on a scheme to the entire scheme. By inversion of a junction. And the precise form of this that we use is again in this 7-author paper. Yeah, and so roughly it gives way to a nice inductive argument. And the idea is we want to lift the splinter property from one of these divisors, which is itself a de Mazur variety, to the entire guy. So lift the splinter property, depending on how I set this up, maybe also I think it should be d w sub 1, the first sort of divisor, to the entire de Mazur. So this is some kind of an induction argument. And the way the inversion of a junction goes is, so rather than fixing a single finite surjective map, it's convenient to go to the absolute integral closure. So yeah, so I'm going to let v x plus to x be the absolute integral closure, and the integral closure of x inside an algebraic closure of its fraction field.
So you're still at the finite case? Or
No, I'm actually doing everything, all of it, affine or non-affine. Yeah, it's an identical argument for all of them. Absolute integral closure. Okay. Yeah. Okay. And so the inversion of a junction, the way that sort of the proof goes is that, and so okay, there's really some boundary pair delta, which I haven't been emphasizing, but you can take your boundary to be any effective Q divisor, which is just less than the canonical boundary that you get by adding up all the codimension 1 de Mazurs. Okay, so you have some boundary pair. Yeah, and what they show in this, when proving inversion of a junction, is that the kernel there's an exact sequence relating this trace map for your divisor to the trace map for the entire de Mazur. So the kernel of the trace map at the level of the absolute integral closure is ultimately coming from a particular cohomology group. It comes from, look in degree dimension -1, absolute integral closure, and then you twist the structure sheaf by the pullback of canonical plus this boundary divisor that we're always working with. Yeah, so here this boundary divisor you should think of as being represented by the element some rationals which are like close to 1. Okay, so we get the splinter property relative to anything that's less than this canonical boundary divisor you get by adding up all the codimension 1 de Mazur subvarieties. And the point is that we have the freedom to choose this divisor as long as it's less than that boundary divisor. And what happens is because this L, the 1, 1, 1, because this is semi-ample, you can pick this delta, and it's really not too hard to do, so that minus kx minus your boundary divisor is in fact ample. Okay. I mean, the point is this thing minus kx minus the actual boundary divisor 1, 1, 1 and so on is or the sum of those codimension 1 de Mazurs is this semi-ample guy L, and so by nudging it something a little bit less than 1, you can pick something that's ample. Okay. Okay, great. And so how do we conclude then? Well, we need this cohomology group over here to vanish, but in Bhatt's paper in 2011, he showed that you do have vanishing up to finite. So yeah, so the last thing goes into the inversion of a junction. I call this thing star. It's that star is equal to 0 by Bhatt result from 2011, which is some kind of characteristic P analog of Kodaira vanishing. So I'll call it Kodaira vanishing up to finite covers. And what this means precisely is that, right, so Kodaira vanishing says that if you have an ample line bundle and you take cohomology of that line bundle below, of the inverse of that line bundle below the top degree, you get vanishing. That's true in characteristic 0, but Bhatt showed that even though that's not true in characteristic P, you can annihilate any cohomology class after passing to some finite cover. And so that vanishing is exactly what they use when setting up their inversion of a junction. So that's really what's going into this proof here. And so, yeah. Okay, so that's how we get, how we do the inversion of a junction. So it actually really just only relies essentially on the semi-ampleness of this particular divisor on the divisor. You might even be able to get away with a little bit less than semi-ample. Okay, so that's how that goes. Maybe I'll say a few other conjectures unless there are questions right now.
Like the Kodaira vanishing does not hold for the Mazur.
Well, so once you prove that they're Frobenius split, I think you do get Kodaira vanishing. But you don't have that before you know. Yes. So actually, once you show that you have the splinter property, all of these vanishing results that only held up to passing to a finite cover actually hold on the nose because everything is a direct sum in something in a finite cover. Yep. Other questions?
So it's at some point you pass from trying to prove global left regularity to proving the splinter property.
Yeah.
How necessary was that?
Well, that's actually a great question. I'm not entirely sure. So it's possible that, so if there is an inversion of a junction for global F regularity that allows Q divisors, you might be able to make that one work. I don't know, the most convenient one we found was the one that you guys wrote up, but yeah. Yeah, but we do get it for a good enough divisor to get global F regularity. Other questions? Yeah. Let me just tell you what we would like to know. So yeah, maybe I'll erase this. So right now I've only been working in equicharacteristic, meaning my sort of local field, E, Taylor-on series T, is characteristic P, and so is the residue field, but we would really like to say something about affine Schubert varieties in the Witt vector affine Grassmannian. So let's say Witt vector flag varieties. All right, so the setup here is now, for example, E is something like QP, and O is the ring of integers. And given reductive group over QP with the Parahort model, you can still make sense of this quotient G mod B. It's called the Witt vector affine flag variety. So it was originally, it is an ind projective perfect scheme. So it's an increasing union of perfections of projective schemes. But so this was first defined by Simonyi, who at least showed that it is representable in some reasonable sense in the Étale topology. And then Bhatt and Schulze showed later that this is really an increasing union of perfections of projective varieties. And so you actually do have affine Schubert varieties inside of here. There's maybe not a great canonical deperfection of them, so you should really think of them as being just perfect varieties. Schulze showed what do I want to say here? Ind perfect projective. It's an increasing union of perfections of projective varieties, but you can't sort of deperfect, or you don't expect to be able to deperfect them all sort of simultaneously. As you go deeper, you have to like take higher and higher p power root things to get sort of your system of closed guys. Okay, so yeah, but so these things exist, and it's a natural question to ask, what can you say about the Schubert varieties inside here? So one thing you might want is you might want whatever property you state to be sort of independent of the deperfection that you choose. And so one property that is independent of the deperfection is something I mentioned earlier, which is ethnopotent. So we conjecture in the same paper that all of these Witt vector affine Schubert varieties are deperfection, well, they are perfections of what are called ethnopotent varieties. So there's a whole field of algebraic geometry where people study singularities and characteristic P based on how the Frobenius acts on various cohomology groups. There's a ton of different adjectives. One of them is ethnopotent. So ethnopotent roughly means that, so it's a local property, so its variety is ethnopotent if all of its local rings are ethnopotent. And a local ring is ethnopotent if all of the local cohomology groups are as small as they could be up to ethnopotent rings. So what that means is that, right, so a ring is Cohen-Macaulay if the lower local cohomology groups vanish. That's one definition. For ethnopotent, you only require those lower local cohomology groups to be annihilated by some power of Frobenius. And then you also require that in the top degree, up to ethnopotent things, that local cohomology group is simple as a module over the twisted polynomial ring where f is one of the variables. But okay, so it essentially means very close to being what is usually called f rational, up to Frobenius nilpotent things. And so this is independent of the deperfection you take of the Schubert variety. And so, yeah, so we also showed it was also, and so the property was already shown in a paper of Bhatt, Blickel, Liu-Resnick, Singh, and Zhang in 2023, that this property of being ethnopotent is the same thing as saying that the mod P intersection cohomology is a constant sheaf shifted by the dimension. And we give a different sort of proof of the same thing in our paper. But so, yeah, so this is what we conjecture about these Witt vector Schubert varieties. It's difficult to prove this though, because as far as we know, there's no good sort of global inversion of a junction for ethnopotents. There are versions of ethnopotents, but they require quite a lot. And there doesn't seem to be a nice global theory of ethnopotents the way there is for some of these other properties. And we really do think that this is the most you could hope for. It turns out to be quite difficult to write down explicit equations for these Witt vector Schubert varieties. Essentially, the only ones we can truly write down are in the few small dimensional examples where they actually coincide with equal characteristic things. Yeah, and I guess so in a few small dimensional examples, the inversion of a junction argument does actually show that the Witt vector Schubert varieties are in fact splinters, but outside of those small dimensional examples, we really think that this is all you can hope for. So that's what we'd like to do. Cool. Well, I think I will conclude there then. So.
Other questions?
So is the splinter property too strong? Or perfections of splinters?
Yeah, it seems that these things are likely not even Frobenius split. Somehow the equations, they just get these really high powers of P in them. And it looks like locally they would violate, what is this criterion for being a Frobenius split variety locally? Yeah, it looks like they would violate that criterion. But actually it's really hard to write down equations. And so we really haven't written down any non-trivial equations, despite trying for a while. But yeah.
So I don't know how it works in the affine case, but at least the classical one, does the same work if you take G mod some parabolic or?
What do you mean by does the same work? Sorry.
I mean, like, do you get the same conclusion with the other splinters?
I guess I don't quite understand the question yet.
It's like you can, instead of looking at G mod B, look at G mod some parabolic.
Oh, yeah. So you can do it for any parahoric. It doesn't have to be particularly any Ohori, as long as it's a parahoric. And also parabolics work in the non-affine case. Yes, because those things are just images of things with.
Okay, so more generally, if you have some vibration and the source is splinter, then target is also splinter.
Well, okay, yeah. So at least for global F regularity, I think you just need the push forward of OX to be O again. I mean, you can. Yes, this property does in fact descend along non-birational things too, just by looking at push forwards of. For the splinter property, it's maybe. Well, again, I mean, you can really get all of these things. All of these things that you're asking me about are. Yeah, there is a smooth projective vibration over them, which has this property. You can get it from that guy upstairs. Yeah.
Questions? If not, let's attempt to edit figure again.